Good morning or good afternoon, depending on where you are at. My name is Tarot Azizi Namini, Director of the ABC UTC, and very warm welcome to March 2022 ABC UTC monthly webinar. A couple of very important information. We recently actually changed the deadline for the abstract for the upcoming ABC conference that will be held during the December 7-9, 2022 in Miami, Florida. The deadline to receive a one-page abstract that you can submit by going to our website is April 12th. So please consider to submit an abstract if you have an ABC related project and you would like to share it with your other colleagues. Another important item is that this conference will be 100% in person. We will not have, it's not going to be a hybrid. It will be fully in person in Miami, Florida, and the hotel is going to be at the Miami Hyatt Regency in the Biscayne Bay. I just wanted to highlight one thing. We have shared with you a number of information related to the conference. In this conference, we are going to have 4 workshops. Each workshop is going to be half a day. And one of them is going to be related to a steel bridge design workshop, one pre-stressed concrete bridge design workshop, one for FRP, composite bridge design workshop, and UHPC workshop. I wanted just to give you a flavor of what these workshops are. These workshops really, just as an example, the steel bridge design workshop is for audience who maybe have been design engineers for some time or engineers that are just coming to the market and they would like to have an in-depth understanding of the AASHTO LRFT bridge design specification as applied to steel bridge design, with the example related to the ABC. So we're going to have a crash course basically on fundamentals of all the provisions, design provisions that's in the AASHTO LRFT bridge design specification related to the steel bridge design, for example, covering the load combination, distribution factor, analysis tool, and many other details like, for example, constructability limited state, SABIS limited state, the strength limited state, estimating FL, and a bunch of other information that really you use in the design. This workshop will also include information that are very important to steel or concrete. For example, in case of the steel, best practices in fabrication, which will be done by Ronnie Medlock, and also the NSBA will provide the list of all the available tools that later you can take to your office and put it at work. So there is also opportunity for exhibit. We hope that you will consider to exhibit at the conference. We can tell you that we are getting tremendous amount of requests for the information about the conference. So it seems like this conference is going to be really a big one because of the past couple of years, people have not had a chance to meet face to face. So hope to see all of you in December in Miami, Florida. And please visit our website and you can get all the information and you can submit your abstract online. You can see all the details about the concrete and the UHPC and the FRP workshop in our website.
Our presentation today features the Washington State Department of Transportation's Precast Concrete Culvert standards for their fish passage projects. We're pleased to welcome our presenters, Mark Gaines, State Bridge Engineer and recently promoted to Development Division Director with WSDOT, and Bijan Khaleghi, State Bridge Design Engineer in the Bridge and Structures Office of WSDOT. We'd like to also introduce our Q&A session moderators, Jugesh Kapoor with WSP USA and formerly State Bridge Engineer at WSDOT, and Paul Lyles, formerly Georgia State Bridge Engineer. We'll now begin our featured presentation. Mark?
Well, thank you, everybody. I really appreciate you joining us today. We're excited to be here. Before we get started, I wanted to thank the ABC UTC group for inviting us here. I wanted to recognize Florida International University for spearheading this webinar series. And also I wanted to recognize the webinar coordinating committee for all their help getting us set up here today. So we are excited to present about our fish passage program and specifically how we're using ABC to deliver this program, because it's really complicated. We're going to share some details on what it's all about and how ABC is a solution we're using to be successful here. I also wanted to mention that we'll have Michael Rosa here from Washington State DOT Bridge Office, and he'll be here as part of the Q&A session at the end to help answer some of the questions. So here's an outline of our presentation today. We're going to give an introduction to the WSDOT Fish Passage Program. We'll talk about ABC considerations for the reconstruction and how we're using ABC to be successful. Then we're going to get into some of the standard drawings that we use for our precast concrete 3-sided and 4-sided structures. Bijan will talk about design requirements for various structures along with delivery, fabrication, and installation. And then we'll talk about the standard plan project we're working on right now to streamline delivery in the future. And at the end, we'll have a couple of example projects for you to take a look at. So the WSDOT Fish Passage Program involves about 3,600 fish-bearing highway crossings. And these are typically small diameter culverts, box culverts that were installed many years ago where we weren't being very careful about considering the impacts of roadway and transportation on the environment, the natural environment. We have about 2,000 fish barriers statewide underneath state highways, and about 1,500 of these block significant salmon, trout, and steelhead habitat. We have a federal court injunction against us that requires us to address an awful lot of these, about 1,000 of them by the year 2030. And there's a couple of pictures at the bottom here that give you an idea of the sort of challenges for salmon. If you're a fish trying to get upstream, you can see an excessive water drop surface where it's impossible for salmon to jump up to the culvert. We have a lot of situations where we have shallow water depth and the salmon can't get upstream due to the limited water. And we also have a lot of high velocity situations where the stream has been constrained such and the water velocity is so high that the fish can't make it upstream at all. And all these barriers really prevent salmon from moving upstream and spawning and basically increasing their population. And the bulk of this presentation talk about how we're using ABC to help address many of these barriers. So just to give you a little bit of geographic orientation here, we're up in Washington State, and the injunction is primarily Western Washington, where we have coastal waters obviously that lead to salmon spawning grounds. And that's what you see in the map there in the upper right. You can also see the map in the lower right. Those red dots, each one of those represents a barrier or a obstruction for salmon. So those are the projects we're working on, is completing those by the year 2030. And you also see a couple acronyms there that you're going to hear throughout the presentation today. So these are challenging projects. A lot of times we're looking at highway detours to be able to build these projects. A lot of involvement in trying to get right of way to complete the construction. And then we get into a challenge of stream bed geometry, scour, and migration of the stream. We have to look at oftentimes rerouting the stream due to hydraulic challenges. And a lot of these are built on poor soils. So the places where we had a 4-foot diameter culvert pipe worked great in the past, but to go to a larger structure, we oftentimes get into deep foundations and a lot of extra expense to make sure we're supporting the structure adequately. We deal with unstable soft soil conditions. Many of these are very deep. We have some crossings which are up to 100 feet below the existing roadway, and obviously there's a lot of challenges to get down that deep and replace the antiquated and insufficient structure. And then of course we're Washington State, so we deal with seismic requirements and liquefaction. And finally, we're really driven by trying to find simple and cost-effective structures. We have hundreds of these to replace, so finding efficient ways to use ABC for delivery is really important to us. So I'm going to go through 3 really quick examples here before I turn things over to Bijan, just to show you the sort of projects that we're addressing here. This happens to be SR 203 Louses Creek, and you can see that is the current fish passage, and fish just don't make it up there. It's too high velocity and it's too congested. So this was addressed using a composite arch bridge, which is 1-foot diameter composite arches, which are filled with cement grout. And then you put a composite decking on top of that, and you backfill it with earth and structure earth walls. And here's a picture of the completed project. Again, this was built very rapidly. We had about a 34-day road closure, full closure of the road to remove all the soil, take out the existing structure, build a new structure, and get it backfilled. So very rapid construction here. Here's another example, SR 532 Church Creek. You can see all the barriers and debris in the way here. There's a lot of woody debris that comes downstream and ends up clogging and choking up this passage. Here's a picture during construction. This is built with a precast three-sided structure to provide a much wider opening to address any sort of debris that comes downstream. And here's the inside of the completed structure. You can see the precast on the outside there. This whole project was built with a 2-week closure, so very rapid construction using ABC. All right, last project here before I turn things over to Bijan, US 101 Coffee Creek. This has 3 galvanized metal barrels, which have very high velocity. It looks pretty stagnant here in this picture, but during the fish spawning seasons in the spring and fall, the velocity through these 3 galvanized structures is too great for fish to make it upstream. Again, built with a very quick 3-sided structure using ABC. And I know you can't see it very well, but if you look closely, that yellow circle there, that's salmon that have actually started going upstream now. And it's pretty neat to see because these have been basic obstructions for fish for decades. And oftentimes the next season after these are built and corrected, we'll see salmon starting to use this new habitat almost immediately. So it really kind of helps explain why we're doing this work. So what I've talked about here is kind of the how and the why we're doing these projects. But one thing they all have in common is ABC, because each one of these has a very tight window of time to get the work done in. Generally, we have to do this work when there's no fish in the stream at all. And for us, that usually means between June and August is our only time to do this work. So we are looking at using everything we can to accelerate how quickly these projects are delivered. I'm going to turn things over to Bijan now, and he's going to talk about kind of how we're accomplishing this and what we're doing to make this an ABC type program. Thank you, Bijan.
Thank you, Mark, and again, thank you, FIU, giving us the opportunity to talk about the structures of fish passage project in Washington State. So I'm going to go through the design phase of that, and also that take us to fabrication, construction, and also at the end, toward the end, before the QA session, talking about the standard plan development as a work in progress, and we are moving in that direction. So the fish passage buried structure, it could be either buried structure or it could be bridges. So when we are dealing with buried structure, there are some advantages, some sites that could go with that. When we have a deep buried stream, can be cost effective, can be installed quickly. Box culvert require no foundation and work well with shallow burial and work well in softer soils. And there are other cases that the bridges could be used. And when we have a shallow stream, unstable stream geometry, limited fish window, and rock or debris moving in the stream, and a longer span, large opening stage construction. So we do both buried structure and bridges. This presentation is focusing on buried structure part of that. So what we did in order to meet this demand on the fish passage replacement structures, culvert replacement, so we came up with the standardization idea because it's a repetition of the same type of work as we go from site to site. So work with the local, we work with the local precaster to determine their forming limitation and match the buried structure, that shape and thing that we are designing with their capability. Initial phases, we had some design that when it wasn't exactly match what they do, so we did have some change order or some redesign. So that was to avoid this standard drawing was to avoid that one. And they document the analysis and design procedure that is used for that. So basically with a beam on elastic foundation for the boundary condition. And in particular, we are using in Washington State because of the seismic zone, we have a racking analysis that is considered. The other thing that we looked at it during this standardization is the range of the span, height, cover depth, and soil properties that we are dealing. We are not covering unlimited properties. We are dealing with the specific type of fish passage demand. So that's how we ranged our span capability based on that. And then the one on the upper corner that you see, these are the fabricators that we are using for this fish passage program that we get together in order to make sure that we are on the same line as we progress with that one. Will Miller from Bridge Office is leading that effort and doing great. Then toward the standardization, also there are several shapers that it could be used, for buried structure. This particular standardization or standard drawing that we developed is focusing on concrete split box and concrete three-sided structure. These are precast concrete that could be fabricated elsewhere and bring to the job site and put it together. What thing we have in mind for all these things is to use ABC concept. Is not coming and digging and forming and casting concrete, those kind of things. These are all precast concrete to meet the ABC requirement. And formwork used for the precast concrete is a span range for the standard plan that we are doing 8 to 35 feet. Conventionally for bridge, anything related to bridge office is 20 feet and above. But then because of the MBI requirement, but for our practice of fish passage, we go whatever is covered, which is way below 20 feet. We are covering from 8 to 35 feet for a standard drawing, but we also have up to 60 feet for a standard drawing that we have in place in use in the office. So these are some of the standard drawings that we did a few years ago, and this is published in our BDM. Standard drawings are available and we are using on fish passage project. We are using consultant and other contracting methods. These are available for all. So these are some of the references to this fish passage standard plans. And here another picture how to put these things together and then how to have the constructability issue resolved in order to get the final product that is a good high quality on that one. Joint is an important factor to come out with a joint that is easy to construct as well as being durable and long-time resistant. So these are standard drawings that we have. It goes with the big tables. This is a part of the table that goes that these are design tables that covering different ranges as well as different geometry and design requirement. So for some of these are shown here for a split box with flat top, we go less than 25 feet. Three-sided flat top span, we go 25 up to 25 feet. Three-sided fixed slope, 40 feet, and three-sided varied slope, we go up to 60 feet. That's covered in our standard drawings. And this is for the assembly of the buried structure. So the main thing, when you bring to this precast segment to the job site, have a good bedding quality that I'm going to talk about that, but also have a method that put these together in order to have a uniform joint and uniform on the top and bottom. So not much of the distortion due to the installation or bedding material and so on. So for this buried structure, the concrete, we are using 5 to 7 KSI concrete, and we are using self-consolidating concrete. It's preferred because it's better flow around the forming that they have. Concrete cover is usually 2 inches and could be 3 inches at the bottom of the precast and buried structure or wing wall footing. And the minimum concrete cover is 2 inches from the deck, unless then, or 2.5 inches when we're using HMA overlay. These are for the cases that the top of the buried structure is exposed to roadway traffic and we are having HMA on top of that. The reinforcing steel is up to 80 KSI that we are using, and we are also using welded wire fabric. This is another way of accelerating bridge construction. The design limit that we have for reinforcing is 75 KSI that we use. For the buried structure design requirement, we are using our bridge design manual, GDM, LRFD, and LRFD bridge design specification, and also LRFD seismic guide specification in general. But there are other documents that we are using also as relate to buried structures and tunnel type of structure that is used for us. Buried structure consists of a split box and 3-sided. Either one of those is a buried structure that's built in a channel and then filled with the soil. So the overall behavior, the final behavior is based on soil structure interaction, is a buried structure with surrounding soil that work together. And then buried structure wing wall and head wall. This is a quick walk through that one. The head wall, wing wall, and railing are designed for vehicular collision and fall protection. And then the bottom of the wing wall is located within 2 feet below the 500 years Scour elevation. So Scour is a big deal in this fish passage program because this is all in Western Washington, is all on the stream bed that we are building this, and the Scour is a big consideration for that. And also a portion of the wing wall below the 100-year mean water surface shall have a reinforced concrete fascia for long-term performance. So not getting much into the design, but just mention one in seismic, because this is specific to our practice. So buried structure, we classify that with the span less than 20 feet, over 20 feet. So as I mentioned earlier, we are covering something from 8 feet to 35 feet for a standard plan, and 8 feet to 60 feet for a standard drawings. But we also have this seismic requirement is applied to the over 20 feet. So in that case, we classified buried structure for 20 feet or less, or 20 feet or more. So that class 2 is the one that we are considering the seismic design. And the seismic design is not covered in the AASHTO BDS or guide specification. So we borrowed that from the road tunnel design specification. So the structure are designed based on 975 years return period, is similar to the bridges 1000-year return period, and is designed based on the safety evaluation, earthquake, SCE, consistent with the ordinary bridge. Basically no collapse. We don't want to bury the structure collapse in it and result the safety on the traveling on top of that. Liquefaction and lateral spread are not considered in developing a standard drawing or a standard plans. So if we have that case, which we do have in some cases, so we do a special design for that. Racking analysis is the one that is used. Again, is based on the tunneling manual and FHWA manual for buried structure, which is a transient ground displacement, TGD using pseudostatic and dynamic soil structure interaction is used. And ground motion attenuation with depth also could be used. That's the table below here that shows if you go that deeper. So ground motion is going to be adjusted for attenuation effect. And the most important is these are buried structures, so we do have the lateral soil pressure as well as the vertical soil pressure. When it goes to the shaking, so we use this combination of 100% of horizontal and 30% vertical, or 100% vertical and 100% vertical and 30% horizontal. This is based on the industry practice that we adopted in our practice. So one thing also specific to us for those buried structures that are exposed to the roadway, we are using approach slab. And this approach slab buried structure typically experience two types of settlement, global and local. The global settlement is a consolidation of the deeper national foundation soil, so this area here. And the local settlement is primarily compression of the field materials directly beneath and upper pavement due to construction. And the approach slab significantly reduces the local settlement with provide the transition to roadway differential settlement, and approach slab may be eliminated in some cases. There are cases defined in our geotechnical design manual as well as recommended by geotechnical engineer, so that when approach slab is too shallow or we have some soil that is not subjected to settlement and so on, so in that case we don't require approach slab. And then we are using also considering the precast approach slab to accelerate bridge construction that make the project faster. We also have a lot of buried structures that are very shallow. So when we have the less than 2 feet from the roadway surface, in that case, provide a structural connection between the adjacent unit capable of transferring imposed shear and equalizing the deflection. The structural connection shall also include cast in place concrete, or in some cases we use UHPC in order to have a more reliable and last longing connection between the precast unit. And the other case, which is also our typical practice for precast member subjected to traffic, that's using a 5 inches minimum composite cast in place concrete on top of that. So if the field depth again is less than 2, we require corrosion resistant reinforcement for that upper portion, unless if you are using the cast in place concrete on top of that, then the buried structure doesn't need to meet the corrosion resistance for that particular reason, but the CIP topping will do the corrosion resistant for that. And also if we have a thinner slab, so then the slab is getting longer, and if the thickness of the slab is 1/20 of the structural clearance span, then we do require pre-stressing on top of the slab. One thing important in buried structure is a differential settlement. So once we put these segments together, as you can see, they become one big unit. And when become one big unit, we may have a transfer differential settlement or longitudinal settlement that could be creating some stresses into this overall structure. So the transverse differential settlement will be considered for service limited state only, and this is basically control of cracking and so on. And then once we get that, then we follow AASHTO for the providing control of cracking reinforcement to the limit of serviceability required. And the structure shall be designed for tolerances 2 inches per 100 foot. So this is a displacement tolerance that we have for transverse differential settlement. When we go to longitudinal settlement, when it's longitudinal along the center line of the culvert, so if there is a settlement that results in joint opening here, so then we do have the allowable joint opening that we follow that one, and this allowable joint opening is calculated based on the Kmax stiffness times the width and then length of the culvert. So make sure that when it's open is within the allowable joint opening that we have for buried structure. One last slide on design is the modeling of these things. So this is again buried structures. We use a three-sided or a split box structure. So in that case, we have a rigid frame with hinge connection at the top of side walls or the footing. So this is the roller and fixed connection in order to get the global stability what we are doing the design. And then a split box construction, and the structure will be modeled as a two-dimensional plane frame with the bottom corner restraint. So the same base as the three-sided structure, the restraint condition is the same. And when we come to the top slab, the upper slab unit of the split box will be modeled as a beam with moment release at the end. So moving from design to fabrication, the fabrication is a very important part of that, that tails to handling and installation of the job site. So we want to do it safely and bringing the final product assembled very high quality. So precast form limitation, corner edge spalling during the stripping, and mated joint offset from wall taper and progressive pre-fitted shop assembly. These are important items that during fabrication to be considered. And when we do the handling, the improper lifting encourage and process and corner edge spall, and then impact damage. So this is the lifting that you can see, or where to put the lifting group and how to assemble this, very important. So the installation challenge is importance of sequence of this put together. Usually they are numbered, and how to be filled on the job site based on the shop assemblies. And pulling a segment together, that's the method that is commonly used. And maintaining compression. So we push this together that the joints are in compression, and also loose bedding material in joints is a concern. So we gotta make sure the joints are clean when we do this assembly. Common fabrication and construction challenges is a bedding preparation. As we mentioned, for this settlement, transverse or longitudinal, the bedding is a very key element, so we don't want to put this thing together when we're adding a weight on top. There's a start settling or something. So the quality of the bedding has the biggest impact on the installation and the quality of final product. Bedding must be flat on the proper grade. High points in the bedding cause gaps in the joint of the top segment, and combination of high and low point cause section to lean to one to other, and the step in the slab. So the bedding material is very important, very competent bedding material, and flat. A couple of slides on the erection of the segment is a leveling adjustment by making adjustment to the bedding material, ensuring uniform bedding, because bedding not only overall, but also we want this to be seated uniformly on the ground, and by side movement. So we want this to be sinking to the bedding, so just be settled without any gap underneath. And the alignment is by jacking at the side of the box, ensuring the jacking load distributed over the large area to avoid damaging, or by pulling or pushing with an excavator. And joint tolerances, as we mentioned about the joints. So this joint is a ½ inch, but plus minus a ¼ inch. But in a real life, that could go more, because we are dealing with a lot of site condition that need to be considered. And inconsistencies on the job site, fabrication tolerance, uneven bedding material, loose materials in joints, uneven horizontal joint, and corner spalling, those kind of things that we should be considered to do that. So the last part of this presentation is a standard plan development, moving from a standard plan to a standard drawing to a standard plan. So this is a work in progress, and we have private industries helping us with this effort. Is developing a standard plan for 3-sided and 4-sided split box, similar to our standard drawing. And the standard plans are very structured. We are using the design code as mentioned here in order of priorities, our BDM, GDM, and then we go to the ASHTO and tunneling references as so. So this again is being designed according to our requirement as well as the national standard for buried structure. So this moving from a standard drawing to a standard plan has other benefits. As Mark mentioned earlier, we have a huge volume of these buried structures that we got to deal with that. So standard drawing is helping us designing in each case, but the standard drawing is going to be pre-designed that could be used directly in construction. So that expedite our project delivery for the ABC consideration, efficiencies in construction and cost, increase quality through repetition and lessons learned, meet project schedule by fabrication and stockpiling, as you can see here. And also because we are dealing with the fish window, so it's contract can go out at any time. Contractor could go to fabrication, stockpiling, and when the time is right to come to the job site and dig the stream and put the segment together. Contractor's familiarity and equipment availability because it's a repetition, and field staff familiarity through repetition and reduce work on agency load because all the work that we do here in-house or consultant to prepare the design will be covered in the standard plans, and so that's a big help for us to do that, to do other projects. Our standard plan is a very similar type of approach as a standard drawing material and properties I mentioned is a class 7 KSI concrete, the class 45 concrete for cast in place, and ASTM 706 or 615. We usually for our practice we use 706, but for precast element we do allow also 615. ASHTO and TERI1. The welded wire also is used to accelerate the fabrication process, as mentioned earlier. And geotechnical properties is important for a standard plan. So this we are working very closely for the geotech office. So the backfill shall be granular material per standard specification, non-liquefiable soil. So anything liquefiable, then we go back to the conventional design on a case-by-case basis. Effective angle of internal friction 34 degrees, and drain internal angle of friction and subgrade is 30 degrees, and at rest air pressure with the K naught of 0.45, and the back slope of 2 to 1 that's used for standard drawing development, along with many other things that not covered here that's used for the structural and geotechnical standard. So in brief, what we are doing on a standard plans is a split box configuration, as you see this figure below and the dimension that are shown. U-shaped bottom with the 10-foot wall plus flat slab on top. This is when the buried structure are exposed to the directly to the traffic or within the 2 feet of traffic. And U-shaped bottom with the 10-foot wall, and U-shaped top with the 5-foot wall. This is a 5 or 10-foot, and also the other one is with the 10-foot wall. And then when we go to 3-sided structure, is a U-shaped top with the 10-foot wall, and then a U-shaped top with 10-foot wall with the CIP stem, and this is the stem on the bottom, and then U-shape top with 10-foot wall, and then a precast stem wall that could be used. So this stem wall could be precast, it could be cast in place. So we will see some example that we are using precasting to accelerate the bridge construction, buried structure construction. So a standard plan sizes and configuration. For a standard plan, the head wall will be 0, 2 feet and 4 feet above the roof line. And for a standard plan, the height of the wing wall will vary from 0 to 2 feet in a 2 feet increment. And then 5 feet to 15 feet with the 2 feet increment, and then 2 options of the back slope behind the wing wall will be considered flat and 2 to 1. That's the back of the wing wall that we are talking about that, and this is the 1 to 2 that's considered over there. So the last slide is last few slides are about the project delivery that we have. Again, is lots of projects. So WSDOT in general is using a different option for project delivery, this fish passage project and buried structures. Design build is our conventional practice that in-house design or design by consultant, we do that. And design build, expedite project delivery and increase innovation opportunities, new material technologies. Progressive design build, this is a new process that's used by WSDOT to facilitate the involvement of the design build team during the earliest stage of the owner's project development. And then contractor supplied design, as are used in some cases successfully. And this is for buried structure with a span less than 30 feet. We do allow that under contract, but also for a span over 30 feet on a case-by-case basis based on approval. We can use contractor supplied design. And WSDOT, we are also participating in FHWA bigger group of project bundling. This has advantages to us. There are several project bundling going on right now in Western Washington for fish passage project that allows efficiency in design, construction cost, engaging a high quality project team and subject matter expert, expedite environmental and permitting process, and increasing quality through the repetition and lesson. So you're going to have 10, 20 or more projects in one project. So this is a lot of lessons learned that could be applied to project. Covering few of this buried structure project. Mark mentioned that these structures earlier, some of these. So the existing the Coffee Creek is one of those, and it was requiring realigning approximately 2,038 feet of Coffee Creek to flow adjacent to US 101, and the culvert that was considered is 36 feet wide and 16.8 feet high culvert. So that allows different fish that goes through the culvert by completion of this project. These are a few projects provided by Michael Rosa, so I'm going to talk about that. The other one is tributaries to California Creek. That one, the undersized culvert, blocked the passage of Coho, Steelhead, and Ciron trout, and two tributary California Creek on I-5, and the newest structure is 18 foot wide and 9 foot one that used for northbound and southbound. So we can see here that's a precast wing wall, and then I'm coming out with the precast footing that's being installed, and then is a split box that put it together, and including the precast head wall and so on. So everything in this job was precast. It's done in a very short period of time to meet the acceleration bridge required. And then SAR 530 Schoolyard Creek. This is the last project, and that one also you can see the benefit of precasting here. That was done on the site, and then bring to the job site, including the precast wing wall and footing, and assemble together to meet the fish passage requirement, and building the stream inside the culvert and opening to the stream flow. That was my last slide, and thank you for your attention. I think with that we are going to the Q&A session. All of us, Mark Gaines, myself, and Microsoft, we are available if there is any question to answer. Thank you very much.
Thank you, Mark and Bijan, for sharing your work with our participants. Jugesh and Paul will now moderate the Q&A session. Jugesh?
Thank you, Marilu. I'm going to ask the questions that came in before the webinar first. The first question is, does Washington State DOT tend to replace fish passage culverts with culverts? Because Oregon tends to use bridges to meet opening standards.
Okay, well, I can answer it. Yes. So we certainly look at the specific situation there and decide if a culvert makes the most sense or a bridge, and it really is site specific. There's examples where we'll have something that's really deep. For example, a barrier that's 100 feet below existing grade, and maybe it's a very modest size opening, like a 20-foot opening, but we find that just because of the complexity of trying to get down that deep to replace a 20-foot wide structure, it makes more sense to put a bridge at that location. So there's a lot of factors. I know Bijan shared some of those at the beginning, but it really does come down to case-by-case decisions and looking at which is the most economical. And we are driven by economics here. If it's less expensive to put in a buried structure, we would take that approach. If a bridge is less expensive, we'd go that direction.
Okay, thank you, Mark. Next question, do you typically work with the Department of Natural Resources on these projects in Washington State?
I can answer that one. So the injunction applies to several different groups. DNR is one of the groups that has a number of fish barriers as well. So we coordinate with them, except they're also addressing their own fish barriers on DNR property. So we're partners with them in making sure we're meeting the injunction requirements. We also have state parks and as another one of the partners that we're working with because they have their own barriers that they're addressing separately.
Okay, thank you. Next question. When these structures are redone, could they make them multifunctional? Example, solar arrays on the top side or filtration / reverse osmosis?
I leave that one to Mark too.
Good question. So I guess we have not really looked at that. I would say that same question could apply to bridge replacements as well. And it's a little bit hard to know exactly what the question's getting at, but we are not doing solar arrays or reverse osmosis in any of our current projects.
Okay, thank you. Next question, are you eliminating fish baffles entirely?
You got all the policy questions up front. I can take that one as well, Jugesh. So the short answer is almost. We are allowed to use baffles, but in very limited situations. For example, a fish barrier that's on very steep terrain and very lengthy, there may be no way to make that work without using baffles to some extent. And we can also look at baffles if you had a situation where trying to retrofit an existing crossing without replacing it. But I can tell you that very few of our projects, like close to zero, actually use baffles. We're always focused on trying to address the barrier without having used baffles because they're not ideal for fish habitat either. So we'll use them when there's no other viable solution.
Okay, thank you. Next questions are mainly on the design side. And the first one is, are there scour issues at the approaches?
What's the question?
Are there scour issues at the approaches?
Yeah, definitely. We have scour issues on the approaches as well. So we do consider scour for buried structures, and then that could extend to the approaches. And this is whether you design the approaches for a scour or not. This is on a case-by-case basis and up to the regions to decide on that. But the scour covered that part.
Okay, Bijan, the next question is, on seismic design, but I think you've covered them. But because these questions came before the webinar, the question really is, what are the special Washington State seismic design requirements for large precast buried structures?
Yeah, as it was mentioned in the webinar, so we are using the tunneling design and modified also by our BDM as well as some industry practices. So we are using the racking analysis for seismic analysis, and we also have a consideration for vertical and horizontal seismic as well, and a combination based on 30%, 100%. We are also considering the seismic performance of the buried structure, including the SSI consideration.
Okay, thank you. Next question, what range of horizontal earth pressure is used in the design of the Washington box culverts?
Yeah, that was mentioned in one of the slides that we have. If I go back to that one. So the horizontal earth pressure is a 34-degree effective angle of friction. And we do a conventional design for the at-rest earth pressure of K0 of 0.445. And also the drain internal angle friction of the P of 30 degrees that we are using, and the back slope of 2 to 1 that we are using for that.
Okay, good.
And
Thank you,
Bijan,
go ahead.
those parameters right there are for the development of the standard plan culverts. We will use site-specific data if we're doing site-specific design.
Yeah, that's a good point. Thank you, Mike. So these are a standard plan. You know, anything that goes beyond that is a site-specific. So this standard drawings or a standard plan do not cover every cases. So those are within the range of the standard. So we can accommodate beyond that.
Okay, thanks for the clarification, Bijan. And Michael, how do you address settlement between precast segments? For example, with use of a bell joint?
What was the question again?
How do you address settlement between the precast segments?
Yeah, definitely. That was covered on slide 26. If I go back over there, yeah, we do have the settlement consideration on the longitudinal direction. We have 2 inches per 100-foot differential settlement that we are considering on the transverse direction, and on the longitudinal direction is based on the joint opening, as I mentioned earlier. That's based on the width of the culvert and length of the segment and so on, and then that settlement is sized to the allowable joint opening. That's what we have.
Okay.
Sounds like they were asking for how we specifically keep the settlement within those limits. Is that something you can answer?
That is my material. Yeah, we want to have a competent bedding material and grade that control this settlement within the allowable ranges.
Between the pre segments, though, we ask the joints between the segments are designed for whatever the imposed shear is across those joints, and we can use shiplap joints have been used before. We prefer more of a shear key approach, or in the past we've used grouted keyways, just to provide that kind of two-way shear connection between precast segments for both longitudinal and vertical joints.
Okay, thank you. Next question, how do these designs in Washington compare to those with Pennsylvania standards?
I can answer that. Oh.
Yeah, we have compared our design with Pennsylvania. We did have some consultation with them, but we haven't done any direct comparison with ours and theirs.
Go ahead.
I can add on to that a little bit, Jugesh. I think what Pennsylvania does is they have a lot of proprietary standard plans that are basically producers that make the products as a proprietary element. And they have those in their library for plans they can use. But I don't believe that they have their own set of in-house standard plan designs that are stamped and ready to go. So the difference in our approach is we're going to have these things basically that if you wanted to build a concrete 3-sided or 4-sided box in the 12 to 30 foot span range, you can basically grab our standard plans and that's all you need to design it. There's no additional engineering required. I believe for Pennsylvania's, although they have the concept down there, there is additional site-specific engineering that has to happen before you can use them.
Yeah, we did have a conference call with Tom Macierci before he retired. So he just explained their process and our process. So this is not really standard plan, but using the industry developed segment to be used for data structures.
Okay. I think I'm going to shift to the questions that came in while the webinar was being presented. The first question was, what kind of foundation was the Lutsis Creek culvert built on? Any scour concerns?
Lutsis Creek was on a spread footing foundation.
Any scour concerns?
A scour was, the foundation is below the scour depth in that particular project. And that's our conventional practice as well.
Okay, this is also a question. The next one is that came in during the webinar. Are wing walls precast also?
Yeah, wing walls are precast as it's shown in last couple of the slides. As you can see, the wing wall here are precast and including the precast footing in this case.
We have used precast, but we also allow the use of structural earth walls in other cases too. So multi wall types, wall types.
Okay. Next question is, it appears that you're increasing flow areas to reduce velocities and improve fish passage. Won't these improvements increase floods downstream?
Maybe Michael or Mark, do you want to cover that?
Oh, I think I can probably take that one. So when we design one of these crossings, we look at those kind of factors. But in general, you can increase the channel that the water travels through, but that doesn't really affect the amount of volume that travels through there during flood events. And floodplain design is part of the consideration. I can mention Louses Creek on that. So that went from, as I showed in the pictures, went from about a 4-foot diameter pipe, I believe, up to a 50-foot wide opening. And a lot of the size of the opening was driven on making sure we could accommodate an upstream floodplain that had been largely neglected. So I don't think that there's any direct correlation there, but again, we're careful to make sure that that's considered when we determine the width of the crossing we need to put at any given location.
Okay, thank you. Next question says, Bijan noted that the box culverts require no foundation. This is true for a 4-sided box on competent soil, but you also have 3-sided culverts. Do they still not require any foundation? And how do you account for load dissemination into the soil?
Okay. Anyway, 4-sided doesn't need foundation because it's sitting on the bedding material directly. 3-sided need the foundation. I can get to that one of those. So these need foundation. That's going to be sitting on the foundation. But when we have the 4-sided, is sitting on the bedding material, as you can see in this picture.
Okay, thank you, Bijan. Next question that came in during the webinar is, does WSDOT try to limit the roadway outage to 4 or 5 weeks?
I would say that that's going to vary based on at each particular site based on the impacts to traffic and the fish windows. So it could be 4 to 5 weeks. It could be less than that. Sometimes we're building these in stages and shifting traffic around the site, either with a shoe fly, or we're shifting traffic and constructing half of the structure at one time. So it varies on a case-by-case basis.
Okay, thank you. With
So,
that, I think I'm going to turn
like
over.
that you can see we had to realign the roadway or come find a detour in order to accommodate that.
Okay, thank you, Bijan, Michael. With that, I'm going to turn it over to Paul to ask the rest of the questions that came in during the webinar. Appreciate your answers. Thank you. Paul?
Okay, thank you, Jugash. And we do have a bunch of questions that have come in, and I'll just try and work my way through them. Is one of them, are you sometimes using post-tensioning to connect the precast segments together at all?
No, I would say no. We use the probably rods sometimes to put it together, tie it together, but not the longitudinal post-tensioning that some others are using to put the segments together.
Okay. Do you use any kind of shear key to prevent your wings from sliding?
Primarily, I think we're treating the wing walls as independent structures to allow for, differential settlement between them. There have been cases where we've tied them, not so much with a shear key, but a mechanical connection. And the benefit in doing that is it relieves the retaining walls to meet some of the same or some of the scour design requirements because they will move and displace with the culvert rather than independently.
Okay. How are stream bed materials inside the culverts designed and sized? Are these are there standards for this, or are the materials at each site just used from the site?
I'm
These
assuming John and do you have an answer for this one, Michael? I was going to have to say we might have to get back to the question on this one, unless you know.
Well, we're not involved in the material sizing inside the structure. That comes from the hydraulic office who does the hydraulic design, and their design is based on what the gradation of the material that they're putting in and whether they're putting in large boulders or woody debris. So, Mark, did you have anything else to add to that?
No, that's what I was going to say is we can get the information from hydraulics, but it's not something we're involved in.
Okay. For four-sided structures, is there a recommended minimum depth the bottom slab should be before the stream bed?
So our
We are using 12 inches, I believe. That's the minimum depth for the bottom slab, but it could be more depending to the size of the box.
I think our scour policy has been revised based on recommendations from the hydraulic office that we're putting the top of the bottom slab 2 feet below the 500-year scour elevation.
Okay. Here's one. How are you calculating scour for three-sided structures? Are you using the NCHRP abutment scour equation plus contraction scour, or are you using the open bottom culvert contraction scour equation?
Scour is calculated from our hydraulics office. I'd have to get back to you on what equations they're using.
Okay. For the 100-foot fill structure, was that replaced with a bridge or another culvert?
Mark had mentioned the 100 feet is as deep as 100 feet. I've seen them as deep as 60 feet. I know we have more coming down the road. I think the Fish Passage program is saving some of the more difficult crossings for later in the program. So I don't think we've addressed those sites yet. That's my understanding.
Okay.
That's right, Michael. They're not built yet. In all likelihood, those will be bridges because trying to get down there and excavate and shore is very expensive, and they're not very wide crossings. So what we're hearing is economically, it generally makes more sense to turn those into bridges because you can spread your foundations out further away from the site and it's basically less costly. Again, we'll drive those based on economics. We'll make sure that we're considering both, but the challenge getting down that deep likely pushes us more towards bridges for some of those deeper crossings.
Okay.
Also, our buried structures, either three-sided or four-sided, has a span limitation, so it's not for big openings. You know, the bridges become more preferable.
Okay. How is water management typically done during construction, and what return period of flows do you consider during construction?
I can take that one in general. So for the most part, since we're within this fish window from June until August, what we're doing is simply collecting the water. The flows are generally pretty low at that time. We collect the water and have a pump and pipe system to route it around the construction site while the structure is being built. As far as the specifics on how those systems are designed and what level of event they would have to accommodate, I don't have a quick answer on that. We would have to look that one up. But it's fairly routine for the contractors to do this. They'll dam things up at one end and have a pump and pipe system to get the water through the job site.
Okay. Have you encountered any fish ladder requirements on the top of the bottom slab? If so, what were they made of? Were they just were they cast into it, or were they fabricated metal or something else?
Yeah. This question for hydraulic and those is not our design, whether using pitch ladder or not.
Okay. There's a question that came in is what measure is Washington DOT using to determine success of this large scale replacement initiative? I'll say you had a beautiful picture of a salmon coming in after you'd built it. So go ahead and take that one.
So I think the measure of success is the amount of upstream habitat that gets reopened to fish spawning. And that's actually what the injunction is based on. Is I'm not going to have the exact numbers, but in excess of 300 miles, 360 miles of upstream habitat, we need to restore 90% of that by 2030. And so we work very closely with our partners, primarily the tribes, the Native American tribes that are part of this injunction, to make sure we're addressing best practices and opening these things up. The success as far as fish returning, that is not a measure we're using to look at success, although anecdotally, it's really nice when you spend money and effort to build one of these projects and address a crossing and you see salmon up there during the next spawning season. So the measure really is the habitat gain we get upstream when we correct these barriers.
Okay. There was a comment here about it. Was there any particular reason for using the concrete option for the buried structures? If concrete option is found to be more cost and schedule effective compared to metal culverts? Or that's the question, I guess. Is concrete option found to be more cost and schedule effective compared to maybe metal culverts?
You want me to take that one?
Yeah, go ahead, you know.
So we're interested in using metal culverts. Right now, we're open to aluminum type box structures, and we're also in general open to galvanized metal plate structures. We're dealing with some concerns in the galvanizing on the outside of the metal plate structures, and we're actively working on this with some of our permitting agencies to make sure if we can find a way to address that. But that is kind of limiting our use of metal plate structures, the fact that they're galvanized, and the environmental concern of having the potential of the galvanizing getting out into the environment.
What I can add to that, our buried structures, our bridge design manual is open to metal as well as other type of material like FRP that Mark mentioned. For this particular presentation, we focused on precast concrete for three-sided and four-sided structures.
Okay, there's one final question I'm going to ask, and for fish passage structures, you need that when you use the three-sided structure with a natural stream bottom, you never use a precast floor slab with those, do you?
No, our three-sided structures do not have a floor slab, and even our four-sided structures, even though they have a bottom slab, we're still filling the culvert with stream bed material. So it's never open to the stream flow unless it actually gets down to that scour elevation.
Okay. It's a quarter after, and this is all the time we have for the question and answers today. So I'm going to turn it back to Mary Lou, and she's going to close out the session. Thank you all. Really a good presentation.
Yes, indeed. Thanks again, Mark and Jugesh, for sharing WSDOT's fish passage projects and precast culvert standards. Very interesting work going on in Washington State. Thanks also to you both and Mike for your thoughtful responses during the Q&A session, and to Jugesh and Paul for moderating the Q&A session. Thanks also to Ali Javid, Ph.D. student at FIU, for managing the web room, and to all participants for your interest, attendance, and your great questions. We look forward to your joining us again for our next monthly webinar on Thursday, April the 21st. And please also remember to submit your conference abstracts by Tuesday, April the 12th. This concludes today's webinar. Thank you.